Welcome to example number 6, the slipping ladder. Suppose we have a ladder that has a weight of 100 newtons and its mass is uniformly distributed across the ladder, and it leans against a wall that is frictionless. The length of the ladder is given as 5 meters, and this floor has a coefficient of static friction of 0.4. We're asked to find how far along from the ladder can this ladder be placed from the wall so that the ladder just starts to slip. So what we want to do is we want to consider a body where we can draw a free body diagram, and hopefully you realize that's going to be the ladder. So let's draw all the forces that would be acting on this ladder. Well, we have the wall that is pushing out horizontally like so. We'll call that the normal force from the wall. So I'll put a little W there. And in the middle of the ladder is the center of gravity, and that's where the weight of 100 newtons is acting. I'll label that as Fg equals 100 newtons. Then along the surface of the floor, we have two forces. We have the normal force that comes from the floor. I'm going to label that as N sub F for floor. And then there must be some inward force to keep the ladder from slipping away from the ground. So this is your frictional force. I'm going to label that as F sub F. I didn't draw any frictional force here because the wall is assumed to be frictionless. Alright, so we're going to choose a convenient coordinate system, and we'll pick our y-axis to be up and our x-axis to be to the right as positive. Now, we can apply different conditions like the force condition or the torque condition. Let's start with the force condition. So we'll develop some formulas here. Let's do the sum of the forces in the x direction equals 0. That means the horizontal forces are going to balance each other out. So we have the force of friction to the right, that is positive, and we have the normal force from the wall, that is to the left. And this is equal to 0. So you can see, by the way, there's two normal forces, one from the wall, but also one from the floor. So the force of friction is equal to the normal force from the wall. And we don't know neither one of these at this point. However, we do know that the force of friction is equal to the coefficient of static friction times the normal force. Which normal force do you think that is? That's the normal force from the floor, because this is the friction force is going to go along with this perpendicular normal force. So this is the normal force from the floor. So we can substitute that in over here. We have mu sub s times the normal force from the floor equals the normal force from the wall. Out of these three quantities, we happen to know the mu, which is 0.4. We also know the weight, which is 100 newtons. Okay, let's move on to the forces along the y direction. We'll come back to this equation. That's a good one to know. We might need that later on. Summing the forces along the y-axis, we see that the upward force exerted from the floor, the normal force, minus the weight of the ladder must balance out to give you 0. So the normal force from the ground is going to be equal to the weight of the board. And the weight of the board is equal to 100 newtons. So now we know another force. The normal force at the floor is also equal to 100 newtons. Which means that we could also find the normal force from the wall. So going down over here, the normal force from the wall will be equal to mu sub s times the normal force from the floor, and mu sub s is 0.4 multiplied by 100 newtons, so this will give us a 40 newton force. So we're starting to get to know all the forces here. We know this is 40 newtons. We know this must be also 40 newtons. And we know this is 100 newtons. So we really know all the forces. think about this problem is we're looking for this distance x. So we need to actually find what? Well, we know the hypotenuse of this is 5, and we're trying to find this horizontal distance. And you know that this is a right angle, but you don't know any of the angles. Let's suppose we were to find one of the angles. Let's say we were to find, I don't know, the angle, here. We'll call that theta. Okay, we want to find that angle, which happens to be the same angle in here, right? Or the same angle over here, because those are alternate interior angles. So really what we need to do is really use the torque condition now. So we're going to do the sum of the torques equals 0. We're going to need to pick a pivot point, and I would choose a really convenient point. I would choose right here, just simply because I have 2 forces here, and I don't have to use, if I pick any other point, then I might have to use 3 forces. So I'm going to pick this point P right here, and so I only really have to worry about this torque and this torque over here. All right, so the sum of the torques about point P is equal to 0. Now the force of gravity is going to cause a torque that is going to make this rod move in the clockwise direction. So this is clockwise. This torque from the wall is going to cause it to go counterclockwise. So this is going to be your positive torque, and that's going to be your negative torque. Okay, so we have 2 torques. We have the torque from the wall, which is positive, and we have the torque from the weight of the board right at the center of gravity here, which is negative. And those 2 torques are being balanced by one another. So the torque from the wall must be equal to the torque from the center of gravity, or the force of gravity. So this would be equal to the normal force from the wall multiplied by the distance, I call it r sub w for now, times the sine of this angle theta, which is up here, which we don't know and we're looking for, and then this force. This is the force of gravity minus this distance r sub g, then multiplied by this angle up here. Now what angle do you think that is? If this is theta and this is 90, hopefully you will realize that this must be 90 minus theta. So this is 90 minus theta in here. 90 minus theta. So really it's the sine of 90 minus theta. So moving down here, just get a little more space, I can start to put in my forces. I know that this force is 40 newtons. The r sub w is the length of this. It's just, you can see up here is 5 meters. So this is 5 meters times the sine of the angle, which we don't know, equals the weight of the board, which is 100 newtons, times r sub g, which is the center of gravity, which would be at the geometric center of this, which would be half the length of the board. So this is 5 meters, and this is going to be only 2.5 meters. In fact, you don't even really need to know the length of the board, really, other than once you find x, because it's just going to be, if this is L, this will be just a half of L. Anyway, sine of 90 minus theta. So on the left side we have 200, and I'll just leave off the units, sine theta, because the units will just cancel out anyway both sides, equals 250 sine of 90 minus theta. And I'm hoping that you're going to start to realize, you're like, oh, I got to find that angle, but maybe you remember something from your math classes. Do you recall something with sine 90 minus theta? Do you remember what that was equivalent to as well? You know, if you do the sine of, say, I don't know, 30 degrees, did you notice that it was also the same as the sine of 90 minus 30 degrees? Was it? No, that's not right, huh? It's the same as actually cosine of 90 minus 30, right? So really, this, or the sine of, say, 60 degrees is really the same as the cosine of 30 degrees, right? So essentially, the sine of 90 minus theta is the same as cosine theta. So therefore, we have 200 sine theta equals 250 cosine theta. And so we really have sine theta over cosine theta equals 250 over 200. And the right side is going to be 1.25, and the sine theta over cos theta is really just tan theta. Hopefully you learned that as well. So tan theta is the same thing as sine theta over cos theta. You should have learned that in your math class. Remember, sine theta is opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. And then so the hypotenuse cancel out, you get opposite over adjacent, which is really just tan theta. Okay, so now that you know tan theta equals 1.25, therefore you can find theta by doing the arctan of 1.25. And that gets you an angle of 51.3 degrees. Okay, that's important because now you know the angle up here in this triangle is 51.3 degrees, and so you just need now to find out this x distance. So if this angle down here is 51.3, and you know the hypotenuse is 5, if we use, say, cosine of 51.3 degrees, it would be the adjacent side, which is x, over the hypotenuse, which is 5. X would be equal to 5 times cosine of 51.3 degrees, which gives you an answer of 3.12 meters. And that's it for example number 6.